Hi Year 14. Today we are going to consider electrochemical cells and we are going to turn to page 7 in our notes. Now an electrochemical cell can be used to produce a voltage from a chemical reaction. If the electromotive force or the voltage generated by the cell is large enough, the chemical reaction in the cell will produce an electric current as soon as the cell is connected to an electric circuit. Now, if we consider for a moment what we actually mean by these electrochemical cells. Let's take a redox reaction, and let's take the one on the screen where we would be reacting zinc with copper sulfate to form copper metal atoms and zinc sulfate. Now, we know that we can take that redox equation, we can separate it up into its two half equations. We have got the half equation there where the copper ion is gaining electrons to become a copper atom, and that's the half equation for reduction. And I'm remembering this oil rig to keep me right as to whether reduction or oxidation is happening. Now, look, if we look at the other half equation then, the zinc atom is losing electrons to form a zinc ion. And we know from oil rig, anywhere where electrons are lost, we've got oxidation happening. Now, if we can take this reaction and we can pop it into an electrochemical cell, we can detect this flow of electrons from the zinc atom to the copper ion as an electrical current. Now, we've got to consider how we would take this reaction and how we would put it into the electrochemical cell. Now, this is where the two half equations are important. Basically, what we are doing is we are setting up each of the half equations in a beaker. So I want to have the zinc half equation. So to get the zinc half equation, we will have in a beaker a solution of zinc sulfate of 1 molar. Now that will provide the zinc ions. Into that solution then we will dip a strip of zinc metal and that will become the zinc electrode. Now that overall in this beaker will be the half equation for the oxidation process. Now the other beaker then we have to set up the reduction half equation. So in the beaker we'll have a solution of copper sulfate of 1 molar, and into that we will dip a strip of copper metal, and this will form the copper electrode. Now our first definition is the definition for electrode, and that's down at the bottom of page 7. Now the strip of zinc and the strip of copper are both electrodes, and what they're both doing are they are establishing electrical contact between a half cell and the external circuit. And if we look again then at the electrochemical cell, like I've said before, each beaker contains the half cell. Now we have got to connect the beakers and we've got to get a complete circuit if we're going to be able to measure the electric current flowing in this electrochemical cell. If we look at the same electrochemical cell, but we are going to consider how we connect the cells. So the first thing that I want you to notice is we have got this salt bridge connecting each solution in each half cell. And remember, that's our zinc sulfate and that's our strip of zinc metal. Then on the other side, we've got our copper sulfate solution and we've got our strip of copper metal. Now what's connecting the two solutions is a salt bridge. Now what a salt bridge is a piece of filter paper and it's soaked in a solution, usually potassium nitrate, and it completes the circuit by allowing the ions to move between each half cell. You'll also notice that we have completed the circuit then as well using electrical wires and a voltmeter. Now the voltmeter reduces the current to 0, and that means that the potential difference measured across this voltmeter is equal to the EMF or the electromotive force of the cell. Now we don't need to be too concerned with the physics of it, but we do need to know that what we are measuring is we are measuring how easily these electrons can flow in this electrical circuit. Now, if we consider the same electrochemical cell, we're just finishing off by applying these half equations. Now, at the zinc electrode, we know that we've got oxidation happening. We said that right at the start. These zinc atoms are giving up electrons to form zinc ions. Now, this zinc electrode becomes the negative electrode. Now, the zinc ions go into the zinc sulfate solution, and remember they can flow across this salt bridge. At the copper electrode then, we know that we have got reduction happening. So copper ions are gaining electrons to become copper atoms, and this becomes the positive electrode. Now, because the zinc electrode is essentially dissolving, it will become smaller, whereas the copper electrode will become bigger as we are making more copper metal at that electrode. And you can see then that the electrons are flowing from left to right. The zinc atom is giving up its electrons. They flow in the electric circuit over to the other half cell where the copper ion is waiting and ready to accept those electrons to form copper atoms. So we can measure this flow of electrons. Now we are going to consider half cells for a moment. Now, the way we measure the tendency of substances to be oxidizing agents, and remember, oxidizing agents bring about oxidation, so they've got to bring about the loss of electrons, so they themselves have got to gain electrons. So therefore, it could be the tendency to be oxidizing agents, or we could say the tendency to accept electrons is measured by a substance's electrode potential. Now, that's the blank that you've got to fill in at the top of page 14. Now, if we consider this half equation on the screen, you can see that the metal ion in solution is gaining electrons to form a metal atom, and that would be a solid metal atom. Now, if we measure how easily this metal ion will accept these electrons, we will measure its electrode potential. Now, the higher the electrode potential, the greater the tendency for this metal ion to accept electrons. You'll notice that the half equation here is written as a reduction, where the metal ion is gaining electrons, and by convention, we will always see the standard electrode potential half equations written as reductions, but it's important to note that these are in fact reversible reactions. They can happen in both directions. Now, if we are this electrochemical series, you will see that actually it is a big list of these reduction half equations, and each half equation is associated with an electrode potential. So on page 14, we're told that the electrochemical series is a list of standard electrode potentials. And you'll notice again that it's in order of decreasing potential. Now, we don't need to learn these. We will be given this information in the exam question, but we've got to understand what the information means. Now, you've got a copy of this electrochemical series on page 15. Now, we're going to add in the labels, but take care as you add in the labels that you understand exactly what you're adding in. Now, we're going to start on the left, and we're going to add the arrow up the left, and we're going to notice that as this electrode potential becomes more positive, the ability to act as an oxidizing agent increases. And remember, an oxidizing agent has to accept electrons, so the oxidizing agent itself will be reduced. So as the electrode potential becomes more positive, we could say that the species is more easily reduced. So the first label that we need to add in is this one. So as the electrode potential becomes more positive, it has more ability as an oxidizing agent, or it is more easily reduced. And if I go then, I can say that the best oxidizing agent in this electrochemical series then is F2, or fluorine. So this is the species in this list that will accept electrons the easiest and will have the greatest oxidizing ability. So therefore I can add an extra label and I could say that each substance will oxidize anything beneath it. So my fluorine is able to oxidize anything that falls below it in this electrochemical series. I'll just add on the T. Now if we go to the other side of the electrochemical series, so it makes sense therefore, that we can discuss it in terms of reducing agents as well. So if oxidizing ability is increasing as the electrode potential gets more positive, well, therefore then it makes sense that the ability to act as a reducing agent will increase as the electrode potential gets more negative. So we're going to add in the label then, the ability to act as a reducing agent is increasing as the electrode potential gets more negative. And remember, a good reducing agent itself will be able to give up electrons easily, so itself will be oxidized. Now if I go then and I look for the best reducing agent, so if the best oxidizing agent was F2 then, the best reducing agent, the one that is most easily oxidized, will be this potassium down at the bottom. So it will give up its electron most easily of all the reducing agents on this list. So therefore, it makes sense to say that each substance will reduce anything above it. So this potassium can reduce anything above it in this electrochemical series.